I think we have to start by apologising to the dairy farmers that will probably watch the recording here, that we had our webinar here today right in the middle of the afternoon milking. So first of all, apologies there, but do hope you get a chance to watch the video. But we want to talk about dairy farms, some 4,000 or so dairy farms across Victoria, and heating up of water is a major cost for them. There was a big push on heat pumps in the late 2000s there, and it was adopted quite widely, up to about maybe 30% of the dairy farms in Victoria. However, it was not a pleasant experience for most. They were often domestic or residential grade heat pumps, and there was a lot of failures and problems with those. And from what we understand from our research, at least 2/3 of those have been removed out of dairy farms, and it does have a bad name, that these lower quality heat pumps that went in there that really weren't fit for purpose. Some people had really nice clean water and clean conditions, and they've survived with their heat pump and they love them, but unfortunately that was not the majority. What we see coming out now is this sort of second generation heat pump, which are much more about a commercial grade, can handle higher temperatures, and really can handle the poorer water quality much better. So it's great to see this next generation of heat pumps coming forward, but still a lot of lessons to learn, and still a lot for that market to develop, where people and farmers have a very good choice of different suppliers in this space. But we certainly see us developing, and a really large potential to help that industry there. So let's dive in and have a look at a case where that has been used. A heat pump of this second generation has been employed and is operating, and have had success and great results. So I'd like to welcome Mario Como, the Senior Project Manager working at the Ellinbank Smart Farm there in Gippsland, along with Greg Morris, the Senior Technical Officer. And so Mario, if I'll get you to share your screen and take us through how you guys went on your journey with heat pumps at the dairy farm.
Do that there. Tell me if you can see it.
We got that one. Go for it. Thanks, Mario.
Okay. All right. Good afternoon, all. Greg and I are looking forward to presenting the hot water CO2 heat pump setup that we set up at Ellinbank Dairy Farm. We'll just share this presentation. I'll get Greg to do an introduction on the farm. So Greg, I'll just hand it over to you. You can explain what the farm actually does.
Yeah, thanks Mario. I just suppose putting it into perspective in regard to, commercial size dairy farm. So the Ellinbank Research Farm, we're here to provide research ready resources. So it's not only for the industry itself, but for a whole group of scientists that do their work out of the property here. We operate the farm on a commercial level, of course. It's a pasture-based system. It's about 175 hectares of perennial pasture. The remaining land is sort of covered with shedding and wildlife areas and riparian zones for creeks and so forth. We do have a 50 hectares of support area. We milk about 450 spring calving cows, so quite important for establishing your hot water supplies is your calving patterns. We produce about 3.1 million litres or 7,500 litres on average per cow per year. So production wise, definitely representative of the industry. And as mentioned, it's a pasture-based system, so probably total of the diet is about 60%, and the balance is grain and other purchased in fodders and feeds. Another big part of the Ellinbank Smart Farm or Research Farm has been a project that we've been looking at becoming the first carbon neutral dairy farm, and I think that's actually in the world. So I know when that was announced by our directors, it created a lot of interest internationally, and it was how we were going to go about doing that. So the big things we've looked at, and energy is one part, but it is also the methane produced by the animals, and that's a big part of what the research farm is focusing on. But As a part of this project, we've actually installed a number of different systems to try and improve energy efficiencies. And that's, I suppose, you know, we've got some lithium ion batteries, some zinc bromide batteries doing different things for transferring water around the farms, for reducing the input costs, obviously. And that's where the CO2 heat pump system, you know, really came into this project well, and you know, and to give us the ability not only to try it for ourselves and to get it working, but to help farmers and be able to demonstrate that these technologies can work, and you know, and what those benefits are really in farm and how they operate. So yeah, thanks, Mario.
All right. So just a heat pump. Why we're using it? So hot water is required to sterilise the piping and equipment after milking. Hot water is required to be above 80 degrees to ensure the system works correctly. So we stipulated on our contract that 80 to 85 degrees was a requirement. So just going through the old hot water system, it was a 2 by 1,250 litre electrical hot water tank system, they were each rated at 24 kilowatt electrical power. We also they were supplied by a preheated LPG gas system and a heat recovery system from the chiller. Hot water delivery was about 2,500 litres. Recovery rate is roughly twice that of the heat pump, so 800 litres per hour. And the new system we installed, which you see on the side there, it's a CO2 heat pump system. It's a 26 kilowatt heat capacity, 8 kilowatt electrical power rated. We put in 2 by 1,500 litre tanks. Refrigerant type is CO2. Heat recovery was removed from the system and diverted elsewhere, and we will explain why we did that. And we call the hot water tank 83 degrees, tank 1, and the warm water tank 2, 60 degrees. The recovery rates 400 litres per hour. So this next slide is just to describe. So what we did, we installed the system in November last year, but prior to November, March, we made sure that we did have energy monitoring that area. So we got a good representation of what energy that we were using. So with this system, we made sure that we got an online system consisting of electrical power consumption, water flow meters, and tank temperatures, for tank 1, tank 2. And that supplied us a good daily snapshot of what the system was, how the system was performing as we installed it. So just the system setup. So this is the system after the hot water's used, and I'll call it system off stage. So tank 2 sits at 60 degrees and is full. Tank 1 sits at 83 degrees and is over half the capacity. And we have a solenoid valve in the closed position. So this is basically at the off time. And so when the system starts to heat, we actually open up the solenoid valve, and we'll explain why we actually do that later on. So cold water comes into tank 2 at about 20 degrees, and that tank 2 water, which was at 60 degrees, moves into tank 1, and that's at 60 to 65 degrees. I've just called it 60 degrees, and the system starts, and it gets to its final temperature stage. Now, it was claimed that we could achieve 90 degrees, and we've gone through the system, and the highest we've achieved is 83 degrees, which is what we require and within our limits. So the tank reaching 60 degrees, tank 2, the CO2 pump system stops, and we have a ready stage position. So the farm, the dairy farm, has the water available, hot water available, and ready to go. So in terms of the issues and solutions, Greg, do you want to start off with the first one?
Yeah, thanks, Mario. So yeah, we're just going to go through, or more so Mario's just going to go through some of the issues or solutions that we had with getting the system up and functioning, and more to the point suit the requirements of the farm. So a couple of the key points, and one of the main ones is what we needed to do here was to establish a backup hot water system. We weren't sure how long the install was going to take. Obviously, being a dairy farm, it's we operate all year round, so we had to make sure we had the correct volume, not only volume, but temperature water to maintain that hygienist system while we continued the milking. We did this just utilising a heat recovery tank that we had basically spare, and made use of the instant gas system that originally supplied the electric hot water services. And look, it really worked well. It maintained that temperature very well. So Mario, I think we're up to you, mate.
Yep. So in terms of the system, so the initial performance of the system, the hot water temperature was well below the stipulated temperature requirement of 80 to 85 degrees for the dairy plant to maintain hygiene. So the first thing we did, we had the heat recovery from our chiller, which was about 52 degrees going into tank 2. So we actually took that heat recovery away, and we're using that heat recovery water in our vat wash system. And that was because the heat pump was switching off. It was reaching 60 degrees on that tank 2 and switching off because of the return loop reaching 60 degrees, switching off. So we then installed a solenoid valve and a timer to divert that water, tank 2 water, into tank 1. And this water needed to be supplied twice a day for morning and evening milking periods in large volumes. We also found that having the system ready for 10 hours, the guys before described a well-insulated tank. The tanks are well-insulated, but there is a temperature loss, whether it be 2 to 5 degrees, that we noticed just looking at our data logger. So we actually made sure that we turned on the system just before we required the hot water. So about 4 hours before the milking period started. In terms of having a backup system in case the heat pumps failed, so we made sure we had an electrical element system in place. So we haven't had to use it, but we can go from auto to manual, and it'll divert to the electrical element system. We also we placed a manual bypass valve, and that was just in case the solenoid valve failed. We could open up the manual bypass valve, and we can shift the water from tank 2 to tank 1, and the heat pump will continue to operate and reach temperature. We also found that we installed an additional outlet in the hot water tank 1, to provide the staff warm water, 60 degrees, because as the system is running, the tank 1 is starting at 20 degrees and reaching that 60 degrees. So they don't have, if you have a water outlet on tank 2 at 20 degrees, it's not doing anything for them. So that was for PM milking and AM milking at low volumes. So in terms of the key learnings, so understanding your system capacity, hot water volume and temperature requirements, that's very important. So with the farmers, you can't expect the farmers to know how much water they need or they've been using. It's mindful that the suppliers or the designers get in there and measure it for them, because you can't rely on their data. And we had good data prior, so we were okay. Understanding electrical consumptions of your existing system is critical, so you can make comparisons and check to see whether the system's performing. Get your CO2 heat supply system and installer which is the plumber in our case, together early to discuss. So I got them both, well, actually Greg, the plumber, and the supplier got together at a local show and demonstrated the unit, and we were quite comfortable and convinced that the system will work. Look at a backup system to maintain existing system, which I've just showed you. Monitor system parameters, temperature, volume, electrical consumption. Now we've got continual data monitoring. This can be done via a BMS or an online system, but if you can't have that system, at least manually check and monitor those numbers, whether it be temperature, a water meter or electrical meter. Ensure that you have a maintenance plan in the system. So there's minimal maintenance on the system. We've done a 6-monthly maintenance check, and it's just basically just checking the overall system, making sure there's no excessive noise, things are running okay. And we've got a yearly maintenance check to do, which will be a bit more on that check. And what tends to happen with hot water systems, they seem to be reliable. They'll run, and it's not until they actually break down that people start having major issues. Ensure temperature sensors are installed in the ideal position and reading correctly. So temperature sensors being installed on top section of the tank compared to the bottom section of the tank can give you different temperature readings. Consider the footprint of the system. Maintain recommended clearances for the CO2 heat pump. So, front, rear, sides, and even the top of it, you should have clearance as per the design of the unit. And work together with supply, installer, and user, and to achieve the result, which is what we had to do. Understand your electrical consumption of the new setup as being the final. So we had no lost time, no issues, but we had a backup system in there, and we mitigated any risk in that sense. So in terms of getting the system up and running, it's been running for about 7 months now, and we're quite happy at the moment. Yeah, that's us for now. If there's any questions.
And thanks very much, Mario and Greg. Yeah, really good summary there. And there's a question come through about the project cost and return on investment. Any sort of high level numbers you can point towards here for the project?
So we know the return on investments. It's quite high. In terms of the project costs, we had to replace the system. So the system was 2002. The original system was 20 years old. So we had to incur those costs. So, for instance, to replace a tank with electrical hot water tank would have been about $17,000 to $20,000. It's equivalent to what the tanks that we got from the CO2 heat pump system. So in terms of costs, I can't give you exact numbers, but we're looking at a payback of 6 to 10 years, and that's taking into consideration the replacement costs being our main instigator in that sense. So in terms of energy savings, we're saving about $6,000 a year. We've completely eliminated the gas. We've got to just go back and check to see how much gas we were using for the farm. I think it's about $3,000. So it's been running for 7 months, so we're just establishing our final numbers, and we'll have those pretty soon.
And of course, on your way to decarbonising there as well. Many thanks for that, Mario and Greg. And I'll go back now and we'll just do a little quick summary. I've got Ahmad just to go through a few of those key issues once more. I think this will steal the presentation back from you. Ahmad, could you just very quickly run us through this one just in 1 or 2 minutes? In the background, Mario and Greg, there's a couple of questions come through. If you could open up that Q&A and feel free to type in a few answers there, that'd be great. But Ahmad, just 1 or 2 minutes on this one.
Sure. So the way we are capturing the important aspects of the lessons actually you guys learned to capture that in our guidance report, we are saying that the understanding of the energy flow, as you said, is a central part again. And most of the your talk, Maria and Greg, was about the water temperature, how important that is, and how it is affecting the entire design. We talk about that in the report. We highlight the maximum temperatures required, and also the thermal storage design and selection and integration of that with the heat pump to be able to maximize the utilization of the heat pump, and also reducing the running cost. You mentioned something very important, that you want to minimize the duration of the hot water remaining in the tank to minimize the heat losses from there. And that's actually an important aspect. We have talked about that about the heat loss of the storage systems in our document. Waste heat recovery, again, as you mentioned, from the milk chiller to be able to partially offset the required heat from the heat pump, and the auxiliary heater, whether it is to increase the temperature of the water to suit the cleaning processes, and also as a backup during conditions that more heat may be required, and the heat pump does not need to be necessarily designed for those extreme conditions and be oversized. Similar to the previous one, if you look at our procurement guide, procurement criteria, you will see that we have emphasized on the quality of the products. And as far as I say, you guys in that project, Ellinbank, have used quality products, as you explained there. So the quality of the products, the compressor, the heat exchangers, especially if it is going to be used in places that might have a higher risk of corrosion on the equipment, are important. We have highlighted them there, but it doesn't mean that other aspects that are in grey there are not important. They are also important too. Jarrod, I believe that was 1 to 2 minutes, so I saved time for the rest of the presenters today.
Oh, yeah. Thanks, Ahmad. We'll make sure we got time for the next one. And just one quick comment there. We hadn't highlighted space constraint, but it did end up being an issue for this one, if considering the microclimate effect. It was always thought for a dairy farm, you're going to have a reasonable amount of space there. But yeah, if you don't have enough space around that heat pump, you'll get this microclimate effect happening and cold air going back into the heat pump and efficiency issues there. So we might need to get space constraint back on there for dairy farm to remind them about that as well. Brilliant. Thanks, Ahmad. And very many thanks to Greg and Mario. And if you've got some questions, they're online, so put them in that Q&A and they'll be able to open those up and answer you there as well.